Welcome to RPI. My name is Sergio Pequito, and I'm an assistant professor in Industrial and Systems Engineering. My research expertise is in dynamical and control systems, also known as stuff that changes over time and that you would like to make it behave in a certain way. To do this, I rely on tools from mathematical modeling, applied mathematics, optimization, and network science. Nowadays, my research seeks to understand how the brain works. This could be in healthy subjects when performing higher-level tasks such as thinking or motor actions. We also seek to understand how the brain activity changes during neurological diseases and disorders. These allow us to propose new diagnostics and therapeutics that mitigate the associated symptoms. Understanding the brain is also key to reverse engineering it to improve technology. Now, let me give you an example of the research performed in my group. In particular, how can a piano guide us in understanding the inner workings of the human brain? When we play a piano, we seek to produce music. To do that, we have to decide which keys to press. Nonetheless, if we want to understand which keys were pressed just from the sound produced, this would be a difficult task as we do not know how each key sounds in a specific piano. Nonetheless, if we have access to the architecture of the piano, such tasks would become considerably easier. This is the same logic we seek to deploy to understand the inner workings of the human brain. In the case of individuals, they react to different stimuli, for instance a sound or a smell, as it does their brain activity when processing a stimulus. To listen to the brain, that is, to measure the brain's activity, we can use this fancy machine. It allows us to see how the neurons that form the white matter tracts are organized. These neurons can be grouped to represent regions of interest. Each region can be represented as a node in the graph where the edges indicate if a neuron crisscrosses different regions. Additionally, we have to keep in mind that some regions will also receive external stimuli. In fact, the machine allows also to track the brain's activities through the oxygen consumption in each region. This oxygen consumption serves as a proxy to neural activity. That is, higher the oxygen consumption, higher the neural activity. By combining the brain's architecture and oxygen consumption, we can infer which stimuli has been provided to the individual. This enables us to understand how the brain encodes a specific stimulus. Therefore, we can contrast how the stimuli are interpreted during health and disease states, thus providing us with new insights that can later be used to propose new therapeutics for neurological diseases and disorders. As an undergraduate student, you are encouraged to enroll in the undergrad research program. How does it work? First, check our research online. Then, send us an email where you tell us about yourself and why you would like to work on a specific topic. Once we find a good fit, you can focus on your research. Now, let me tell you about a project where a freshman student worked with me in quantifying alertness. In this study, subjects were exposed to different light wavelength and intensity, and their brain waves were collected over time. After cleaning the data, we proposed a new methodology that extracts features pertaining to dynamical systems analysis. Specifically, we can assess how alert subjects were upon the oscillatory behavior across different brain regions. Quantifying alertness is a stepping stone to develop lighting schemes that will help workers maintaining their alertness. For instance, drivers, soldiers, and medical personnel whose lack of alertness can lead to life-threatening events.